And hello everyone, Paul here again, and today we are going to continue our discussion of the motions that the Earth and the Moon go through. Last time we left off with rotation, which remember is the Earth spinning on its axis, and remember we have two different kinds of day. As a result of that spin, we have a sidereal day, which is the Earth spinning around one time, or we have a solar day, which is noon to noon. And if you're confused about that, go back and listen to the last part of the last lecture again. And we will continue on though. And so revolution is the Earth spinning, or rather, sorry, got that wrong, didn't I? Rotation is the Earth spinning, and revolution, on the other hand, is the Earth going around the sun. We go around the sun once every 365.25 days. Obviously, maybe that 0.25 is why we have leap year. Every 4 years, we have to add a day to our calendar to get it to all kind of work out. We're moving pretty fast, about 66,000 miles an hour. By the way, with the rotation, I don't remember if I mentioned this or not. If you're standing on the Earth's equator, going around, you're moving about 1,000 miles an hour. You're moving around a 24,000 mile circle. At a 24,000 mile circle in 24 hours, and that comes out to 1,000 miles an hour. Now, as you move away from the equator, that speed gets slower, because if you're just standing at the pole, you're just kind of spinning in a circle. You're not really moving. And so here in Pinellas County, we're moving about 800 miles an hour just with that spin. We're moving around the sun at the same time at about 66,000 miles an hour, with an average distance of about 93 million miles. Okay, and so our planet follows Kepler's first law. It follows all of them, but right now the first law, which means that our orbit is an ellipse. And so there is a point when we are closer to the sun, called perihelion, and then there's a point when we are further from the sun called aphelion. Here, give me just 1 second, and I'm going to draw that for you. Okay, so let's take a look at what this looks like, right? And so here's the sun. I'm drawing. Oh, I'm not drawing. Am I drawing? There we go. Okay. Hold on, let me get rid of that, y'all. Here's the sun. I cannot draw. Bear with me. Okay. So here's the sun. Okay. And so the Earth's orbit around the sun is an ellipse. Now I'm going to draw. Well, stop that. I'm going to draw a very exaggerated ellipse to make a point here. So bear with me a little bit. That's not great, but it'll do. Okay. So this point right here, when we are closest to the sun, is called perihelion. Okay, this point out here, where we are furthest from the sun, is called aphelion. Okay, I try to remember A for further away, A for aphelion. That helps me remember what's going on. Perihelion is just the other one. Okay, now maybe you're saying to yourself, okay, wait, I get it. This is summertime, right? Because we're closer. No. Let me erase that. No, that's not summertime. Okay. The seasons, by the way, are reversed in the northern and southern hemispheres, right? So when it's summertime up here, it's wintertime in South America and Australia, and we're all going around the sun at the same time. And also, it's not even true. When it's summertime here in North America, it's just by sheer dumb luck. We're out here right now. We're out here. So no, okay, it's not the distance from the sun. The other thing is, y'all saw that drawing of, the actual drawing of the Earth's ellipse around the sun. It's not, it's a circle. I mean, so no. If you thought that we were closer to the sun in the summer and further in the winter, unlearn that. I'll replace it with something else here in a few minutes, but unlearn that. Okay, so there is no up or down in space, right? We think of up as away from the surface of the Earth, down is toward the surface of the Earth, but there's nothing like that in space. And so in order to measure things or talk about things, we need to really kind of just define a plane somewhere or another that we can talk about when we talk about directions or where something is in space. And what we do with that, the plane that we define, is called the plane of the ecliptic. And so, and what this is the plane that the Earth orbits the sun in, right? And so I'm going to draw it kind of down here. It's most useful to draw it from the side. I'll show you another view of it here in just a second. But so once again, I'm drawing, so y'all bear with me. I'm terrible at this. I'm bad at it on the board, much less on a drawing pad. So anyway, if that's the sun, and this is the Earth out here, okay? The plane of the ecliptic passes from the center of the sun through the center of the Earth and then out into space as far as you would like it to go, right? And what it does is it gives us a very handy reference plane for talking about where things are, because all of the 8 classical planets are more or less in the plane of the ecliptic. So Mercury, is more or less in the plane of the ecliptic. Venus is about the same size. I have a massive scale issue as I'm drawing these things, by the way. Mars is, they're all mostly in the plane of the ecliptic. I don't have room to draw Jupiter, Saturn, Uranus, or Neptune, but they are mostly in the plane of the ecliptic. Now, I said 8 classical planets because Pluto, a dwarf planet, is not in the plane of the ecliptic. Pluto, that's the symbol for Pluto, is inclined. Pluto's orbit is inclined 17 degrees to the plane of the ecliptic, which is one of the things that got Pluto in trouble, kind of got Pluto kicked out of the Planet Club. And so we'll talk more about that when we talk about dwarf planets. But Pluto, Eris, another dwarf planet, is inclined 45 degrees to the plane of the ecliptic. So, but most, like I said, the inner 8 planets, the classical planets is what we call them now, are all orbiting in the plane of the ecliptic, right? And so here's what the solar system looks like, right? You got the sun in the middle, and then tightly spaced up against the sun, you got Mercury, Venus, Earth, and Mars, okay? Asteroid belt, Jupiter, Saturn, Uranus, and Neptune. I like this drawing for a couple reasons. But one of them is, here's the thing about this. Every drawing you've ever seen of the solar system is having to make compromises, okay, in terms of scale. There is no way to draw the solar system to scale properly and have it fit on one piece of paper. It just won't. These orbits will shrink down to where you can't see them. These orbits are so spread out you can't fit them on the paper. If you draw the planets the proper size, they're actually the sizes of these stars in the background, and so these are way too big. But if you drew them to scale, you wouldn't be able to see them. And so later on, I'm going to have you all watch a video or show you a video where they do construct a proper scale model of the solar system. And if the Earth is the size of a marble, you need miles and miles to fit the solar system. And so it's not easy to do. This diagram, though, does make compromises. They all do, but it's still pretty good. First of all, notice how the outer planets all have rings. That's because they all have rings. Jupiter has a ring system. Saturn, Uranus they all have ring systems. Inner ones don't. You can see Pluto. Pluto's right there. You can see Pluto's orbit crossing the plane of the ecliptic at 17 degrees, right? Uranus is orbiting on its side because Uranus is on its side. And they've kind of shown these little swoosh marks behind the planets to show that they're orbiting this way, right? They're going around the sun counterclockwise as viewed from above the Earth's North Pole. You have to specify that, otherwise you just don't know. So what this means, though, for us on the Earth is that if you're looking for a planet, that planet is going to lie in that strip across the sky that runs east to west, right? It's going to be, the planets, the moon, and the sun all follow the same path across the sky. And so watch where the sun goes, and then watch where the moon goes. That will also be where the planets go across the sky. So I cannot tell you how many times someone has pointed to the north and gone, oh, look, there's Venus, right? No, that's an airplane or something, okay? Venus will never be in the northern sky, okay? Venus is going to rise in the east and set in the west and travel along the plane of the ecliptic as viewed from the Earth across the sky. So in that sense, it kind of narrows it down a bit as to where you can expect to find planets. Once you know where that is, that's that's where that is. Not going to talk about that, but let's talk about the Earth's axis of rotation. So, so when you look at a globe, you'll notice that it's tilted. The Earth is tilted relative to the table it's sitting on. Okay, they tilt that axis of rotation. Now they don't tilt it because it looks good and artful. Okay, they tilt it because it's tilted. Now, once again, we're in space, so tilted doesn't really make much sense if all you say is tilted. Tilted relative to what? And what it's tilted relative to is the plane of the ecliptic, right? And so if that's the Earth's axis, so the Earth is spinning counterclockwise around that axis, okay? And here's the plane of the ecliptic, so that's going to go through the center of the sun. All right, so there it is. The Earth's axis is tilted 23.5 degrees, right? That's what causes the seasons, is that tilt in the Earth's axis of rotation. Because what happens is, I didn't draw the equator, but the equator is going to be right about through there, okay? And so what's happening here is the northern hemisphere is tilted toward the sun. So it's getting more direct sunlight, generating more heat. The southern hemisphere is tilted away from the sun, getting less direct sunlight, generating less heat. So summertime up here, wintertime down here. In 6 months, the Earth will be on the other side of the sun will be over here. Now the northern hemisphere is tilted back away from the sun, less direct sunlight, less heat. Wintertime, opposite down here. We're going to do a whole thing about seasons when we do meteorology, so don't worry if you're not quite following now. Don't need to. It'll be fine. Okay, so now here's the other thing though. If the Earth's axis is tilted, then as it spins, that axis is likely to move. It's likely to kind of go around kind of like a top almost, right? So it's tilted, and then that axis spins around. Actually, yeah, it spins around. Okay, it takes it 26,000 years to go around one time. Okay, and so right now, and this motion is called precession, which you can see there. Right now, there's a star over the North Pole, Polaris, or the North Star. It will tell you which direction north is. It will also tell you your latitude, by the way. But as this precession continues, okay, what will happen is gradually the North Star becomes not the North Star because the axis moves off of it, and then 13,000 years later we're over here, and now Vega will be the new North Star. In between, I don't know if there's stars in there. I mean, there are, but I don't know if there's exactly stars in there or not. But this takes 26,000 years to go around one time. Takes a long time. Remember when I was talking about the ancient Egyptians and I said, look, when they lined up those pyramids, there wasn't a North Star. This is why. Right, 4,000 years ago, when they were building those pyramids, the axis was like over here or something. It wasn't right under the North Star, which is a bazillion miles away, but it's still sitting over the Earth's North Pole. So precession is something that not a lot of people know about. Every now and then you'll hear something about it, but not a whole lot of people know about precession, but nevertheless, there it is. Okay, now, let's turn our attention, though, to the moon. So the moon goes around the Earth about once a month. This is where the word month comes from. A month used to be a cycle of the moon's phases, right? From new moon to full to new, and then again. And that cycle takes 29.5 days as the moon goes around the Earth, right? That's what originally a month was. Then a bunch of Roman emperors got a hold of our calendar and did weird things to it, and now it's all messed up. But originally, if you're making a calendar from scratch, and you all know I'm obsessed with calendar making, if you're making a calendar from scratch, one of the easiest ways to mark time is by the phases of the moon, and that time through one cycle of those phases is a month. Now, more exactly now, it is a synodic month. Which is going to be the time from one new moon to the next new moon. That is going to be different, though, from a sidereal month, which is the time it takes for the moon to go one time around the Earth, right? They're different for the same reason we have a solar and a sidereal day because the Earth-Moon system is going around the sun. Let's take a look at an animation to help explain this. Okay, so let's see how this works. So here we have the sun, the Earth, and the Moon, with the Moon sitting more or less in between the Earth and the Sun. We'll talk here in a few minutes about moon phases, but we can see here that, with the Moon in between the Earth and the Sun, half the Moon will be lit by the Sun, but that's not the half facing the Earth. Well, what we see from the Earth is just no lit Moon at all. In fact, and it's sitting from our point of view very near the Sun, and who wants to look at that? Also, massive scale issue here, but I think y'all figured that out by now. And so what I'm going to do now, so this is the new moon, right? You don't really see the moon, okay? This is traditionally kind of the beginning of that lunar cycle. Now, what we're going to do is I'm going to run this, okay? And they're going to keep a red dot right there as they move the Earth-Moon system around the sun. And when it gets back to that red dot, it will have gone around one time, around the Earth one time. So let's take a look. So we do that. And give it a minute or a few seconds. There we go. Yes, there's a line. They're lined up. And now, right? And right? It just went around the Earth one time. That's 360 degrees, and that's a sidereal month. Okay, that is the moon moving around the Earth one time, one geometric 360 degree time. But notice, is not lined up between the Earth and the Sun because the Earth moved around the Sun. That geometry changed a little bit, right? And so so now it needs to go for 2 more days to get back in between the Earth and the Sun. And so we do that, and and now it's the new moon again, right? And so now it's a synodic month. Right now, it's gone through an entire cycle of the moon's phases. Okay, and so I'm going to just run this and talk for a minute. And so, from the last lecture, we learned about solar and sidereal days, and this one we just learned about sidereal and synodic months. Okay, in both cases, sidereal is simply geometry. Right, it is either the Earth spinning or the moon going around the Earth, but in both cases, sidereal is 360 degrees. Okay, and then there's 2 observational things in the case of, and I'm going to pause this here in a minute. In the case of the sun, that's a solar day, okay, which is from noon to noon, okay, and then in the case of the moon, that is a synodic month, which is new moon to new moon, okay. Those are observational things. Those are things that anyone can see, whether they know how the Earth goes around the sun or not. You're still going to see that stuff. Okay, and so so once again, sidereal is geometry. It's 360 degrees. Either the Earth spinning 360 or the moon going 360 around the Earth. Okay, and then and both of those are sidereal, right? And then observational things: a solar day, 24 hours, right? And a synodic month, which is 29 and a half or 30 days. Okay, all right. Let's go back to the PowerPoint. And so here's a drawing of it, which I don't particularly like because that star is far enough away that these lines should really be parallel. I don't know why they do it like that, but they did. So anyway, I think we've got it. If we don't have it, shoot me an email and let me know. Okay, so let's think about the moon though. So there's the moon, and that is definitely what you are used to seeing. When you look at the moon, that's what you see. Now you might not see all of it. You might see this half or that half, or a little sliver over here, a little sliver over there, or something like that. But that's what you see. Okay, you have never looked up at the moon and seen that. In fact, that might be the first time a lot of you have ever seen that. That is the so-called dark side of the moon, although it's probably better to call it the far side of the moon or the other side of the moon or something like that, because there are times, as you can see here, when it is completely lit up. Okay, but no, you never seen that. You see this. So what I'm saying is that that the same side of the moon always faces the Earth. All right, so let me say that again. The same side of the moon always faces the Earth. And so my guess is, if I say that, what you're thinking now is, okay, that must mean the moon doesn't spin. Let's see. So here's another one of my animations. So here's the Earth. I put in for North Pole, so we're looking down on it. Here's the moon. I divided the side you can see from the side you can't see. Put a little M there for moon, and we're ready to go. So let's put it in motion around the Earth and not spin it. Looks like that. Well, wait a second, right? Over here, on that side, I can see all of that other side of the moon. And in fact, as if it's not spinning, as the moon goes around the Earth, we're going to see all of it, right? We're going to see the whole thing at some point or another. So it's not that the moon isn't spinning. And in fact, the moon needs to spin, and it needs to spin in such a way that the same side always faces us. In order to do that, the moon's period of rotation and its period of revolution are going to be different, okay? Or rather, I'm sorry, are going to be the same. Okay, if it takes it 30 days to go around the Earth, it's going to take it 30 days to spin. And so let's see what that looks like. Oh, well, it looks like that, right? That makes sense, right? In the time it takes it to go around the Earth, it also spins, right? And so now that same side always faces us. So until you go up there and you fly around that back side, you're not going to know what's there. And we didn't know what was there until we went and literally flew around the back side. Okay, and so yeah, now that would be a remarkable coincidence, right? And it's not a coincidence. It's called orbital locking, and it happens. Things that are spinning in gravity fields gradually do slow down. The Earth's spin is slowing down very slowly. It happens. Gravity exerts a force that slows down rotation. Okay, and so it makes sense that the moon would slow, but the moon is locked, right? And you can see what I mean by that. And it's locked way too early. It ought not have locked yet. And so we want to ask ourselves the question: why has the moon locked so soon? Well, if we look at pictures of both the near and far sides of the moon, we begin to get an idea, right? Because without knowing what anything is, the near side has all of those dark parts, right? And the far side does not. And you can read the words, so you know where I'm going with this. But here's the thing, right? So July 1969, Apollo 11, Neil Armstrong and Buzz Aldrin landing, Mike Collins orbiting, landed right there, right about there, more or less. Okay, they brought back rocks. Apollo 12 landed right about there. They brought back rocks. Apollo 13 was supposed to land there. They didn't. An oxygen tank exploded. They made it back, but they weren't able to land. Maybe you saw the movie, really good movie with Tom Hanks, Apollo 13. Okay, so Apollo 14 landed there because Apollo 13 couldn't. Okay, Apollo 15 landed up here. I do not know offhand where 16 and 17 landed, but they landed somewhere around here. Okay, so yeah, but they all brought back rocks. And when geologists started looking at the rocks, they were like, hey guys, the rocks from these dark parts are lava. These are lava flows, right? And by now we'd been around the backside a few times orbiting and knew kind of what was back there, and we began to understand that there aren't these back there. And you're like, look, these lava flows are making that one side of the moon heavier. Now I put heavier in quotes because it's in space. It has mass, not weight, but whatever. It's in a gravity field, so it kind of does have weight. But anyway, heavier, right? And so our gravity has latched onto that side of the moon and yanked it toward us and will not let it go. And so as the moon goes around the Earth, that same side always faces us because it is heavier. It's got those lunar maria on it, and so it is locked maybe sooner than it should have. All right. Now, continue on to think about the moon. Let's talk a little bit about phases. So sometimes when you look at the moon, it's a little sliver. Other times it's full. It is not bigger when it is full. Here's maybe a better picture showing what's going on. You don't see it at all. And then sliver, bigger sliver, bigger, 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 biggest, big, fully lit moon, and then small, 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 small. Notice though, right, you're always looking at the same side. It's just a question of how much of it is lit, right? Remember that same side always faces us. Okay, so what's going on here? Well, first of all, let's go back to this picture because this is interesting. Right, this full moon is a larger photograph than the crescent moon. So meh. Okay, but every now and then you will see on the horizon something that looks like a really big full moon. Okay, and people, oh well, the atmosphere is magnifying it, or maybe it's a super moon. No. It is an optical illusion. And it's interesting because it's one of the oldest optical illusions we know of, but no one really knows why it works, right? Most times when your brain misfires with an optical illusion, a neurologist can tell you what's going on, right? Here's why your brain thinks that dress is blue when it's really gray, or here's why you think this is moving when it's really not, right? A neurologist can explain that. The moon illusion is something that they can't explain. They don't know, but it is. If you were to measure the angular distance of the moon, as you saw it, just take your fingers and put them on either side of it, right? And then hold your fingers there for a few hours until it was higher up in the sky, and do it again. It's the same size. When it's close to the horizon, sometimes your brain misfires and thinks it's really, really big when it's just normal size, but your brain is misfiring or something like that. So anyway, so this is what it looks like, right? So sliver, bigger sliver, etc., down to nothing, and then it starts over again. So a lot of times people look at this and go, well, that's the Earth's shadow. No, that is not the Earth's shadow. Okay, my sister thinks that. Stop it. Okay, that's not the Earth's shadow. It's something else. But what else is it? Well, let's take a look at an animation to explain this. So here is our lunar phase simulator to help us understand what's going on here. And so as I look at this, we can see, so the sun's over here to the left. Here's the moon here, and then here's the Earth, right? Here's what the moon looks like. That is not lit. That is fully lit. Okay, so there's what the moon looks like. And then this shows us where the moon and the sun are in the sky. Okay, so when it's sitting here, more or less in between the Earth and the sun, the phase is new. Half of it's lit, and half of the moon is always lit by the sun. Always, always, always. It's just a question of how much of that lit half can you see. Well, here, the half of it's lit, but it's facing the sun, not the Earth, and so we see the dark half, and that's what it looks like, right? Now, plus, by the way, let me move it just a wee bit. The moon in the sky, from our point of view, is very near the sun, and no one wants to look there. So you're just not going to see that. Okay, now, but let's go 2 weeks later. Now the moon is over here, right? And now it's nighttime, so we can see it. Okay, moon's over here, right? The lit half is still facing the sun, but now because it's on the other side of the Earth, it's also facing the Earth, right? And so now you look up in the sky and you see a fully lit moon. Okay, fully lit half of the moon. And so yeah, now in between, can't see it at all and see the whole thing, there's this whole phase bit going on here. I'm going to speed this up a little bit. And so you get the idea now that as the moon goes around the Earth, we gradually see more and more of that lit half until finally, when it's exactly on the other side of the Earth from the sun, we can see all the lit half, and then we start seeing less and less of the lit half as it continues its way around the Earth. Okay, the moon is in the sky as much during the day as it is at night. It's just not as easy to spot during the day because it's not nearly the brightest thing in the sky. Okay, so half the moon is always lit by the sun. It's just a question of how much of that lit half can we see from the Earth as it goes around the Earth. Okay? Alrighty, back to the PowerPoint. Okay, so there's what I just said in words. You've got it in your notes, or I suppose you can pause the video and write it down if you really want to, but there it is. Okay, so commonly people think that those phases are caused by the shadow of the Earth, but they're not, right? They're caused by the moon going around the Earth, making that visible side less and then more lit. But sometimes that shadow does cross. Sometimes, right, the Earth and moon line and sun line up perfectly, and we get shadows crossing, right? When that happens, that's an eclipse. Now, there's two kinds of eclipse. There are solar eclipses and lunar eclipses, right? With a solar eclipse, the moon is blocking the sun, and so it's casting a shadow on the Earth. And if you're in that shadow, you're going to see an eclipse. Okay, here's what it looks like. So let me draw down here what's going on, okay? And so hold on one second. Let me turn my finger on here, and let's go with a pen, and let's change the color because I like the white. Okay, so what's happening here? Actually, I'm going to draw it up here. And so once again, I'm about to draw. It's going to be terrible, and we're going to have a scale issue. Okay, so bear with me. But and so if this is the sun, once again, sorry. And so with a solar eclipse, this is the moon here, and this is the Earth here, okay? And so what's happening is the moon is casting that shadow on the Earth, and if you are in that shadow, you see the eclipse. You see this, right? They are spectacular, they are amazing, but that's what's happening, right? They're lined up perfectly. Here's another one, looks like that, right? Now, every now and then, you'll get an eclipse with the moon at apogee. So the moon is maybe a little, not too hard, a little bit closer to the sun. Not much, not that much, but a little bit. Okay, when that happens, what you get is called an annular eclipse. Looks like that, right? The moon doesn't quite cover the sun, right? Through a remarkable coincidence, and it really is just sheer dumb luck. The size of the moon, when viewed from the Earth, and the size of the sun, when viewed from the Earth, are the same. Now, the sun's a lot bigger, but it's also a lot further away, so they look like they're the same size from our point of view. If you move the moon a wee bit closer to the sun, it looks like that, right? Just a little bit. That shadow's not that big, by the way, and if you're not in it, you're not going to see it. So it's a very small shadow. Solar eclipses, this is not something that, all the world is watching the solar. No, they're not. No, they're really not. Okay, and it's a very small shadow. Right, here's a drawing of it, better than mine. Right, there's the moon, there's the shadow. If you're in this part of the shadow called the penumbra, you'll see a partial eclipse. If you're in the umbra, you will see a total eclipse, and that's a very narrow strip. Where you can see that eclipse. Here's a map of eclipses from 2001 to 2025. I'm gonna have to get a new map soon. But when I first got it in 2004, it seemed like I had plenty of time, right? But remember this one back in just a few years ago in 2017. There was that one. Okay, here I think it was about 80 or 90% eclipse. The closest it was to you guys here was in South Carolina. Here, yeah, so my family live in Charlotte. My mom, my dad, my sister, her family all live in Charlotte. So I drove up there and spent the day before the eclipse watching the weather, right, and going, okay, where is it likely to be clear? right? I ruled out the coast. There was weather coming in there. I said, I think Greenville will be good. And I called a friend in Greenville and I said, hey, are you watching the eclipse? And she said, heck yeah, I'm having an eclipse party. Bring your telescope. And so I did. So we had an eclipse party. It was a great fun. Looks like that. It was amazing, y'all. Just amazing. I don't have the words to describe it. I really don't. It gets dark. It gets cold. The stars come out, okay? And where the sun should be, there is an inky black hole in the sky. It is just indescribably amazing. And the reason I'm telling you this is I really want you, if you can at all, to drag your butts into totality, okay, into the path of an eclipse. There is one coming up in 2024, okay, just a couple years away. It's going to go up through Mexico, across, and then come out, across the U.S., and then kind of the Great Lakes region, Maine, etc., right? Find some nice weather along this path and get into totality. It is incredible. It really just is. And so, yeah. And if you can't get 2024, hold on. I got another one for you. 2045. I've not even done the math to know how old I'm going to be in 2045. I don't want to know, okay? But I'll get out there with my electric wheelchair, my walker, my telescope. I'll be watching the eclipse, y'all. But here it is, right? I don't know if we're in totality here or not. But go to Gainesville. They're going to be right there. They're going to be right there. And so, yeah. But I mean, seriously, if I didn't have to like earn a living, I would be chasing eclipses all over the world because they are phenomenal. They really are. So that's a solar eclipse. That's kind of what we're used to, or rather, when I say the word eclipse, that's what we're used to, right? And so I'm going to draw on here again. Give me 1 second to get that set up. And yeah, oh, good. It's still white. Okay. And so I'll put it down here. And if this is the sun, I still can't draw, y'all. So bear with me. And this is the Earth. I'll put a cross in it because that's a symbol for the Earth, right? Solar eclipse is over here, right? So there's the moon casting a shadow on the Earth. When you look at it, you're seeing the moon block the sun. Lunar eclipse is the moon is over here, right? Now, the Earth's shadow is falling on the moon. I can't draw it. You get the idea, though, right? And so now what we see, this is also the moon over here. And so I'm going to label, and this is solar. This is lunar. And so what we see then is the Earth's shadow crossing the moon. Okay. Now the fun thing about these is everyone gets to see it. There's no path for it. As long as it's nighttime where you are, you can see the eclipse, okay? And so right here's what these look like. There's the moon, and we can see the Earth shadow. This takes hours, by the way. Solar eclipses, you blink and you miss them. Lunar eclipses, that shadow crosses and takes a long time. You can watch it. You can take pictures of it. At totality, it gets red. People freak out. Oh, it's a blood moon. Yeah, whatever. It gets red. Okay, it turns red because at this point, all the light hitting it has passed through the Earth's atmosphere. Okay, and so and the shorter wavelengths, the blues, get filtered out. The longer wavelengths make it through, and so what you end up with is a moon that looks red. Okay, because it's reflecting red light. Now, here's what this kind of looks like drawing, but I'm going to do another drawing. So let's think about this, and this is the last thing I want to talk about. So once again, here's the sun, here's the Earth. I know they're not the same size, okay, and here's the moon. I'm going to put it in two different places. I'm going to put it here and I'm going to put it here. Okay. So we learned two things, right? When the moon is more or less in between the sun, that's a new moon. Right? We've also learned that this position here is a solar eclipse. I don't have any board skills even on the internet. Okay. It's a solar eclipse, right? Then we learned over here this is a full moon and a lunar eclipse. right? Every single solar eclipse has to happen during the new moon. It just does, because that's where the moon is when it's in between, right? You're never going to see a first quarter moon crossing the sun. The first quarter moon isn't here. It's over here somewhere. Third quarter moon is over here somewhere if we're looking down on it. Okay, and so yeah, no, right? Oh, I deleted the Earth, didn't I? Let me do it again. Hold on. So every single, I'll make it bigger. Oh, well, heck. Okay, so now it's great with respect to the moon, but terrible with respect to the sun. Oh well. And so anyway, so yeah, every single solar eclipse has to happen during the new moon. It just does. And every single lunar eclipse has to happen during the full moon. It just does, because that's where the shadows are. Okay, but now we're wondering why, and I'm going to erase these because I'm going to draw some more. Why isn't there a solar eclipse every single new moon and a lunar eclipse every single full moon? Because right now it certainly looks like there should be. Okay, so why isn't there? Okay, well, here's the trick. Okay, so if you're thinking that we're looking at this from above, switch your perspective and let's look at it from the side. Okay, so if we look at it from the side, let me draw the plane of the ecliptic, right? So remember that too hard. The plane of the ecliptic runs from the center of the sun through the center of the earth and then out into space as far as we would like it to go. Okay, as I have drawn it here, the moon is orbiting in the plane of the ecliptic. Here's the problem. It doesn't orbit in the plane of the ecliptic. The moon's orbit is inclined relative to the Earth's, in other words, relative to the plane of the ecliptic. It is inclined 5 degrees. I drew it too big. That's okay. That's the least of my drawing problems. 5 degrees. Okay, and so these shadows usually miss. The moon's shadow will miss the Earth, and the Earth's shadow will miss the moon usually. Okay, there are 2 days a year when it could line up, when we could get an eclipse. Okay, so what you do is you ask yourself on those 2 days, is the moon new or full? And if it is, you'll get an eclipse. Right? Here's a better drawing of it, done by Paul Spudis, and some words done by Paul Spudis, a great lunar geologist. We lost him just a few months ago. But Paul Spudis knew more about the moon than anyone alive. I mean, he really did. And in fact, he's written a very good book called The Once and Future Moon. If you or someone you love is interested in science or interested in the moon, it is an amazing book. And so you can see how he's got it here. Here's the Earth. There's the sun off to the right. So here's the plane of the ecliptic, right? The plane that the Earth orbits the sun in. There's the tilt of the Earth's axis, 23.5 degrees. He drew it on the equator. That's fine. If it's tilted on the equator, it's tilted. If it's tilted at the axis, it's tilted at the equator too. But there's the moon's orbital plane, right? Tilted 5 degrees relative to the ecliptic plane, right? That's why now the Earth's shadow, in this case, is missing the moon, and why when the moon is up over here, its shadow will miss the Earth, right? 2 days a year when it could possibly not miss. The question is everything else going to be in place too? Okay. Okay. And once again, that book, The Once and Future Moon, it is a great book. It really, truly is. Okay, that'll wrap us up for now. You all take care, and I will talk with you again soon. All right. Bye-bye, everyone.